Hello, welcome to SPWLA Nuggets of Wisdom, the wonderful world of resistivity from the micro scale to the macro scale. I'm Roland Chemali. I'm technology consultant for Well ID. Well ID is a Norwegian company. I'm located in Houston and I consult for them remotely. If you have any questions about this presentation, do not hesitate. You have my email addresses shown here. So the wonderful world of resistivity will cover all these topics: resistivity logging and water saturation. This is the main application of resistivity logging. Water saturation is a euphemism for how much hydrocarbon we have in the formation. Then there is a special section for a class of reservoirs called laminated reservoir, where resistivity anisotropy plays a special role. Then we will go into the micro scale with borehole imaging, where the micro resistivity provides vivid images of the formation, which are very prized by the geoscientists, geologists, and petrophysicists. On the macro scale, we go back to macro scale. Well placement is a unique application for resistivity is key to well placement, geosteering, and reservoir mapping. And then finally, a safety moment, which will be how resistivity can help with geostopping, the resistivity at bit, and more recently, since I would say the last couple of years, looking ahead of the bit. There are articles in the Petrophysics Journal on that subject. So resistivity can be seen as a Swiss Army knife. It has multiple uses. It has um, can openers, it has saws, it has scissors, it has bottle openers, and it has a knife. So it's a Swiss Army knife with multiple uses, and resistivity can be seen as a science which has multiple uses. So let's go to the let's start with resistivity logging and water saturation. That is by far the first application and still remains a very important application to resistivity. It all started with Schlumberger in Pechelbrunn in September 5 to be precise, 1927. You can see here a truck which is either the truck that was used at the Pechelbrunn well or maybe a similar truck. You can see that the logging engineers are wearing ties. Wow. And the logging operator has a umbrella just in case it rains. This is the first log that was ever recorded. It is a piece of museum. So where is Pechelbrunn? Pechelbrunn can be seen here uh, in the northeast part of France, just at the boundary between France and Germany. And it's near Luxembourg, it's near Belgium, and it's near let's see, Brussels is here. You can see Stuttgart, you can see Strasbourg, and you can see Frankfurt, and Paris is here. So it is located in the heart of Europe, but it is very important historically because this is where the first log was a resistivity log. The first log was a resistivity log. Was 15 to 20 years after the Pechelbrunn event, a gentleman by the name of Gustav Archie uh, tied resistivity to porosity and water resistivity in formations. He did a lot of measurements on cores and found that some kind of a law correspondent, the much maligned Archie's law, which we all know as RT equal RW over phi square in its most simple form. RT is the resistivity of the formation or the core, and RW is the resistivity of the water that's filling the pores, and phi is the porosity of the formation. It later became more general by changing 2 into M being a cementation exponent, which takes into account the tortuosity of the pores. So for highly tortuous pores, M can go as high as 3. And for, let's say, loose packed sandstone, it will be M can go as low as 1.5, but the default value is 2. So for petrophysicists, RT equal RW divided by phi to the power M is our E equal MC square. So remember that we are not in the business of drilling for salt water. We are in the business of finding hydrocarbon. So he introduced the water saturation SW as being the fraction SW to the power N, N being the saturation exponent parameter is equal to A. N is default to 2. A is defaults to 1. It's a fudge factor coefficient. RW, again, the water resistivity. Phi sub M, phi is a porosity, and M is the exponent of cementation factor. And RT is the resistivity of the formation. So you can get water saturation if you know all the other parameters, which we usually do. Porosity is a different log we use, and RW is known through either samples or from SP or other local knowledge. RT is what the resistivity tool measures. So after Archie came Simondou, who had a couple of equations, and then Poupon-Levaux, uh, who came up with other equations, the modified Indonesian, which was also a Poupon-Levaux deal. The dual water was a type of equation that was invented by Clavier, Coates, and Dumanoir in the late 70s. I happen to have known all of these folks. I even worked for Chris Clavier for several years. And then Juhas was with Shell, and he followed the path that Shell had followed, which was using the cation exchange capacity QV. So you have multiple equations for interpreting shelly sands or complex formations, which were invented by several great petrophysicists. I got this list from the Interactive Petrophysics User Guide software. Interactive Petrophysics is a very well-known package for interpreting logs. Thank you, IP. But what I want to bring up here is I would like to cite my last boss at Occidental Petroleum. His name is Kent Newsham, and he's the chief petrophysicist at Occidental Petroleum. Kent is a great believer. At first, he's a great expert in mudstones. He wrote 3 fantastic tutorials that were published by the journal Petrophysics, a very prestigious journal. And in it, he describes a workflow for interpreting mudstones or unconventionals. And for resistivity, he uses Archifiti, which means he just takes the total porosity and assumes there is a single water resistivity in the formation. And I have applied it. I have applied his technique many times, and it works very well. So I just wanted to thank you, Kent Newsham. There are others. Waxman and Smith introduced initially the concept of cation exchange capacity to account for shale. Poupon had others. Then there was Bussian, then there was Worthington, and then there was Dirk Timur and others. So all these eminent petrophysicists were working in harmony, and I'm saying that in jest. They really spent a lot of time arguing with each other, uh, not sometimes at the limit of what is acceptable, but it was so funny to attend some of the SPWLA symposia in the 1980s, it was more like a circus more than anything else. So let's take a quick break here. So we are on a break. We are resting, and now we're going to pursue with how do we measure resistivity in order to get water saturation for the petrophysicist. So let's get back working. The resistivity logging by itself, there are many ways. Uh, Typically, lateral log type for water-based mud and induction log type for both water-based and oil-based mud. And then in LWD, there is the LWD family, and then a short word about uh, what happens in microwave frequencies. So let me start with the lateral log. I stole this from my friend Clive Johnson. This is a model for using for the lateral log. You have a sound in the middle of the borehole. You have a survey current and focusing electrodes. And the focusing electrodes are here to make the measurement as sensitive as possible to RT. Remember, we are after RT. And on the way, it will find an invaded zone and a possibly a transition zone. So the design of the lateral log is to try as much as possible to see RT. I got this. This is the drawing that I borrowed from Halliburton, and this is a map of potentials and currents that I obtained from Schlumberger. So I like, when I discuss lateral logs, I like to go back to the original dual lateral log, which was designed by the folks in Schlumberger Richfield SDR in the 70s. And it consists of an electrode array that had deep lateral log and shallow lateral log. And the idea is that by combining the two, you can um, try to get RT directly. So here you have a shallow lateral log with all the currents returning on the sound itself, and a deep lateral log where all the currents return at the surface. Um, in addition, in order to be able to invert and be able to get RT, the scientists at Richfield SDR, Schlumberger Dow Research, uh, invented a pad type tool which will be very sensitive to the invaded formation, RXO. And it was called the micro SFL, microspherically focused log. I was there at the time. I wish I could claim ownership. No, it was invented, designed by a certain Charles Regal, who invented the whole array in 1 week from beginning to end, and it was tested, and it immediately gave excellent results. You will still find the MSFL logs everywhere. So how do you use this whole contraption? Let's suppose originally the inversion was done by a chart. It required a very sharp vision. Uh, since the 80s, the inversion started being done by a computer algorithm, as you might have guessed. So let's suppose that you have the deep lateral log and the micro SFL, and you read the ratio, and the deep lateral log versus the shallow lateral log. So here is an example. RLLD is 20, RLLS is 10, RMSFL is 2.90 meters. And you get this point here, which will tell you that RT is in fact 27 ohm meters, so it's higher than both RLD, RLLS, and it tells you how much RXO is exactly RMSFL, and you get the invasion diameter. So it was it was quite that tool had a lifetime of about maybe 20, 30 years, I would say 30 years, and you will still find dual lateral log logs in the files. The dual lateral log suffered from a one major drawback. It had a tendency to find oil when there was none, and that was called the Groningen effect because that's where it was first observed in the field of Groningen, and it was simply due to the fact that if you are below a big, thick anhydrite or salt, the deep lateral log would start reading high resistivity, much higher than expected, way below the right into the juicy part. So the bad part about that is that it gave a false indication of oil. And you had a lot of logging engineers running to the asset manager and saying, boss, I have found you the best oil field in the world. And then soon after that, you drill a fantastic water well. I was personally taken to task by Turk Timur from Chevron, who told me, because of your expletive Groningen effect, I drilled a X million dollars water well, and you'd better do something about it. He even carried the message to higher ups, and Schlumberger was the first one to come up with an array lateral log, which would do away with the Groningen effect. That was the main reason people moved from the dual lateral log to the array lateral log, is because with the array lateral log, you had no current return at the surface, and that eliminated the whole problem of Groningen effect. So the array lateral log measurement is much more trustworthy than the dual lateral log. The other service companies followed suit. So here is an example that my friend Casey gave me. In an array lateral log, you have multiple uh, depth of investigation of the curves, and then you run an inversion. When you see a very shallow measurement, a medium measurement, a shallow measurement, a medium measurement, and a deep measurement separate, that tells you that you have invasion and that you will need to do some serious processing. The same thing here, to do some serious processing to get RT. And that is very powerful because RT here, you will know, is probably higher than 2000 ohms, which is with an invasion. That means you probably have good permeability and probably a good reservoir. So that is the array lateral log. There is a company in Stafford, Texas, which is a suburb of Houston, called Oliden Technology, that took the array lateral log onto an LWD collar, and that would be ideal for cases where you have very saline mud and fast invasion. Then in oil-based mud, and now also for water-based mud, you have induction log is run much more frequently than the lateral log. This is kind of a interesting because because the induction log was initially designed by Henry Dahl from Schlumberger to be specific to oil-based mud, but then later on they realized that, my golly, this thing works also in water-based with the proper design, and that was a big success story. So the array induction, which was really the work of my friend Thomas Barber, has from Schlumberger, has a coil, a transmitter which establishes electromagnetic waves, and a bunch of receivers that are combined in pairs to give you multiple depth of investigation and multiple resolution. So an array induction typically will have one transmitter, multiple receivers, multiple frequencies, multiple depth of investigation, real-time processing and post-well processing. But it's also used in oil-based mud and water-based mud, which with that power, the induction is probably the wireline tool that is run in most of the wells in the world. I'm talking about resistivity. So here is an example of a reinduction log that I got from a Schlumberger publication. So you have here the multiple investigation, and you have also the different resolution. So you get here a resolution of 1 foot, either at the well site or process, or 2 feet or 4 feet. And you have a depth of investigation of 10, 20, 30, 40, and 90 inches. Very powerful tool. In the 90s, or maybe possibly in the late 80s, a gentleman by the name of Rich Medder had the idea of uh, putting an induction on a drill collar. It sounded so far-fetched because most physicists thought you can never put an induction tool on a drill collar. But Rich Meadow had a great idea, and he managed to create an induction on a drill collar. He used propagation instead of balanced coils, but it was the same equations, and the whole LWD industry took off from the moment that this LWD propagation resistivity became available. I just want to make a quick diversion. What happens at microwave frequencies? At microwave frequencies, resistivity is very much subdued as compared to at regular LWD or wireline frequency. In other words, if in the lab you take a core and you measure it at 1 kilohertz or 10 kilohertz or 20 kilohertz, you'll get a certain resistivity. But then if you go to the gigahertz range, which is your microwave oven, then you will get a much lower resistivity. And that's known as the resistivity dispersion. There are few publications on that. I cite here a paper by Wang and Popit from Chevron, 2013, where they show this is the array dielectric tool from Schlumberger with frequencies going from 1 gigahertz to 2 megahertz, and it shows how the conductivity, which is the inverse of resistivity, varies with frequency. So now if you are, let's suppose you use Archie's law for a measurement done at 1 gigahertz, you will miss 2/3 of the oil that's in place. That's why at the gigahertz frequency, giga means 10 to the ninth. At gigahertz frequency, you cannot use Archie's law. You have to use the CRIM, complex refractive index method, and that is the equation for the CRIM. And I have published in 2025, I have co-authored a paper with my friends at WellID, where we show that uh, the resistivity at which we call the Archie resistivity at frequencies of, let's say, megahertz or less, can drop significantly. In this case, let's say from about 15 to about 4 or 5 when you go to 3.8 gigahertz. So be careful when you see resistivity in the gigahertz range, you cannot use Archie. The next is, I'm going to talk about laminated reservoir and anisotropy. If you can pronounce the word anisotropy, you are way ahead of the game. So there are a lot of formations which are deposited in layers. Uh, Turbidites is such an example. And you can, these layers can mess up how you interpret Archie's formula if you're not careful. So for instance, in this case where we have a sand shale sequence, if the sand is 10 ohm meters in green and the shale in brown is 1 ohm meter, which is very common, then what you will find is that if you run an induction tool, you will measure RH, the horizontal resistivity, it will be 1.8 ohmmeters. If you could measure the vertical resistivity, it would be, because now the layers are in series in the vertical direction, it would be, instead of 1.8 ohmmeter, it would be 5.5 ohmmeters. So the anisotropy is a clear indication of layering and a, let's say, a strong suggestion of the presence of hydrocarbon. Baker Atlas was probably the most proactive in that domain. So they designed something called the 3D induction wireline, and then the other service companies followed suit, where you would measure RV and RH by using coils that are oriented uh, to measure horizontal resistivity and vertical resistivity. Why this whole anisotropy, in fact, started before we could measure it. Before we could measure it easily. In the 1990s, Jim Klein and his colleagues and uh, some people also from Schlumberger who were looking at logs from the Kuparuk, that's up in Alaska, noticed that their interpretation showed less oil than the core analysis would show. And that made a big difference in the evaluation of the company called Arco, because Arco was a big part, I mean, Kuparuk was a big part of Arco's assets. So Jim Klein thought about anisotropy and how it could be used to better assess the oil content. And once he did that, he showed that he can increase the value of the amount of oil that's in place significantly, and to the point that they match the core analysis. That's not Jim Klein, possibly his cousin, but I know Jim Klein cannot jump this high. Even then, he could not jump this high. I took Jim Klein's method 20 years later for a field, maybe it was a Kuparuk or a field near the Kuparuk, where we noticed I was working with petrophysicists and geologists from Pioneer, and we noticed in a vertical well that we were reading RH equal 2 ohm meters. Then in a high angle well, we were reading a much higher resistivity. By doing some inversion, we found that RV should be 7 ohm meters. Look at this contrast. That told us that this is layering and that the sands are probably very likely to contain oil. So we applied Jim Klein's method to see what happens. And we computed RH and RV in that formation. Uh, and we found a fairly big contrast, about a factor 5 between the two, 5 to 7 between RV and RH. And then we applied the Jim Klein method to determine saturation. And lo and behold, we got a oil content, which is phi times 1 minus SW, showed here in blue. And uh, at the same time, we had cores and we that are here, and we smoothed the cores phi times 1 minus SW, and we got a great agreement between the two. So anisotropy is something you don't find it everywhere, but it's much more common than people think, because many of the reservoir are deposited in layers, and relying only on RH would send you would underestimate your reserves. Now we go to the micro scale to borehole imaging. Uh, Borehole imaging, I'm going to go into 4 directions. Borehole imaging, wireline, water-based mud, then wireline oil-based mud. Then I'll go LWD, water-based mud, and LWD, oil-based mud. It all started with my colleague and soon to become boss at Schlumberger. His name was Stan Genzero. He and I are still good friends. Um, I distinctly remember a flight from New York to Paris in the 1970s, where it was a red eye. All the flights from New York to Paris are the red eye. And I was seated next to Stan, and he was busy drawing pads and buttons, and I was busy trying to get to sleep. So when I woke up, I had had a good night's sleep, and he had a good patent in his name. Um, Here is Stan. Then he was kind of he was good looking at the time. He still is good looking, but that's him now, retired in California. So this was a concept, a pad with multiple buttons focused into the formation, and you convert that into an image. And if you look at, we're almost 50, 40 years later, you look at the different pads, different microelectrical imaging, wireline for water base, you will see that they all follow this idea. So this is for wireline water base mud. And you get this is an example from my friend Clive Johnson. Please don't tell him that I stole it from him. So here is the microelectrical imaging using resistivity wireline base mud. So you can understand. I'm not a geologist. I know the geologists get all excited when they see that stuff because they can see the laminations, they can see the layering, they can see the unconformities, and they get all excited. I, as a petrophysicist, I try to extract resistivity from that. So one day I had a conversation with my friend Oberto Serra from Schlumberger, and I asked him. He was a big proponent of this measurement, and I asked him, "Why are you so excited about it? It doesn't even give you saturation." And he told me in French, "La saturation, je m'en fous," which in polite English is, I don't give a flip about saturation. And the rest is history. So I realized at the time that this tool is really um, primarily for the geologists, but also for the petrophysicists. Because when you see something like this, you realize immediately that you cannot just apply Archie blindly. You have to use some inversion for anisotropy. So then after that, oil-based mud became the rage in the 80s, 90s, and up to today. And the service companies designed uh, based on similar principles, but quite different, the imagers for wireline for oil-based mud. Here are examples from Schlumberger, Halliburton, Baker Hughes, and Weatherford. At the same time, with the ability to measure wave propagation and resistivity by rich metal, LWD became also the rage. And microelectrical imaging in LWD water-based mud became possible in the late 90s, early 2000. And it was a success story because there were benefits to LWD imaging in the sense that you had full borehole coverage. The difficulty was that the pad itself or the sensors had to stay very close to the borehole. But you can see from the various papers that continue to come out that LWD water-based since the early 2000s have been quite successful. But then you come to the real challenge, and that was LWD oil base. and that took decades to crack. The first example that I can relate to was from a publication by Schlumberger in 2018. You can see here this example in oil-based mud. And for all transparency, I'm a consultant for Well ID in Norway. Well ID managed to take a totally different angle, a totally different approach. And using a miniature radar, they are able to image 17.5-inch hole and bigger in LWD. This is an example which they published around 2020, 2023, I think. So one word about this invention, the microelectrical imaging using radar in for LWD oil-based mud. The patent is in the name of Lars Oy. He's the inventor. He's also the CEO of Well ID, and the patent was issued in 2021. And you can see here the initial team of Well ID. This is the tool. You can see the four uh, pairs, the four transmitters, receivers, which are miniature radars. If you measure the round trip time between the transmitter, the borehole wall, and back at the receiver, you get an idea of you get a caliper, high accuracy caliper. And if you measure the attenuation, then you get a electrical image. Here is a view of the the radar-based caliper. You can see the spiraling, which is very often seen when you have rotary steerable. We continue now with the next subject, which is well placement, geosteering, reservoir mapping, reservoir navigation, all that with resistivity. So that's the macro scale now. We are on the macro scale. And why do we geosteer? Why is it important that we geosteer? And for geosteering, really resistivity is the way to go. I submit to you 3 examples. The first one is based on an OTC paper, OTC 17110, that was by Equinor, Statoil Hydro at the time, in the Troll field. Because of geosteering, Statoil says that they were able to recover an additional $2.4 billion worth of oil, which is quite considerable from the Troll field. Another example, it was in a small meeting. John Hampson from Chevron Alba stated that they obtained another $225 million worth of additional production from 3 wells thanks to geosteering. The third example is unbelievable. It's the man on the street knows about geosteering. You may not like the political views of CBS, or you may like them, but that's not the object here. CBS 60 Minutes, which is a very widely watched program, went to interview the then chairman CEO of Saudi Aramco, Al Juma. And this is how the interview went. And you listen for yourselves.
That easy, according to Aramco CEO Juma.
It takes a lot of effort. The oil is a gift from God. The recovery of oil is really the work of men, and this is part of it here.
Here in this room, Aramco engineers are making sure that not one drop of oil is overlooked. These computers are receiving data via satellite from sensors mounted on drill bits that are burrowing deep into the oil fields all over Saudi Arabia. The engineers are sending IMs, instant messages, that actually guide the drill bits.
He is now directing that drill bit to go into the best areas of the reservoirs and suck that oil from it and not leave any oil behind.
So in
and
other
supply.
words, this drill bit's like a snake.
It is
He doesn't
exactly.
go like that.
No.
It would go down and then
And
follow where
yes,
the oil is.
absolutely. And mind you, this is happening 400 to 500 miles from here geographically, and we are sending that drill bit also 2 or 3 miles in the ground.
Al-Juma says with this technology, they're able to recover 10 times more oil than before.
So here you have it, 10 times more oil because they follow the reservoir, which is a layman way of saying geosteering. Geosteering with resistivity is done through LWD azimuthal. LWD because you need to react in real time. And azimuthal is because this is the most effective way of seeing boundaries. The whole thing is based on a patent by my friend and distant cousin, Michael Bitar. He's now director of technology at Halliburton, and he patented in 2002 the idea of using tilted receivers and tilted antennas to be able to sense boundaries and be able to detect them way before you come close to them. The, Conceptually, geosteering in conventional reservoirs is based on a simple image. You imagine here that you have an oil producer that's high on the structure and a water injector. As the water drive, as the oil water contact climbs up, you sweep the oil effectively. Now, if the oil producer had been low on the structure, then as the oil water contact rises, you will start producing water and you will leave attic oil behind. And that's not a very desirable situation. That's why how you place your well is very important for the ultimate recovery of the oil. Now, if you were in a situation of a gas drive, it would be reversed. You would want to keep the producing well close to the oil water contact. The concept geosteering uses a entity called geosignal. Geosignal is like the signal from a metal detector. Geosignal, which comes about in tilted coils, tilted receivers, detects approaching boundaries from the side, so you can get if it's a conductive boundary, you get a strong signal. And we simulated that during my days at Halliburton, where we hang a real tool high, well above a test tank or a swimming pool, which contained well, it was not a swimming pool, but it was a big test tank with 0.20 meter. And we monitored the height above the test tank surface, and we computed what should be the reading and the geosignal reading. And we plotted here in continuous line the model results, and the continuous line, the model results for the up bin and the down bin. And then the measured points fell right on the predicted points. I have very seldom seen such an agreement between theory and experiment. So that tells me that we are on the right track. Here is an example that we published, a paper IPTC in 2009, where the paper was proactive geosteering in thin reservoir bound by anhydrite in Saudi Arabia. The operator wanted to make sure that we could maintain the well within a 10-foot bed. And we said, of course, let's try it. So here is you have a density image here. You have a geosignals here from different spacings. And this is what we conceived as being the path of the well and the up and down boundaries. So the density image, the azimuthal resistivity image, the geosignals from different spacings, the porosity logs, the gamma logs. And as we landed the well, the geosignal started out pointing up, saying there is a conductivity above you, which is correct. Then, as very soon we noticed that the geosignal went to zero, which told us that the geosignal from above and the geosignal from below were equal. We were in the mid bed, in the midpoint of the bed. We didn't expect to find it so soon. That's because the bed, instead of being the promised 10 feet, ended up being only 5 feet. So at that point, we decided to immediately build angle and try to pull up. And we started seeing the low resistivity below the bed, and we said build angle very quickly, pull up, and we crossed the midpoint again. By that point, at that time, we had already drilled more than enough to prove that we can stay within a normally 10 foot, but here we did it within a 5-foot bed, and we had qualified the service. So we went to the secondary objective and we exited the formation from above.
Eugène Breinaert is 87. Hij heeft een auto en een garage. Alleen de combinatie van die twee is een beetje krap.
Mijn auto die is 1,49 meter. En mijn garage daar is 1,55 meter. Dat doet hem 6 centimeter, zie. En door heb ik dan de moes aangedaan. Tegen een moest tegenrijden. Dat ben ik kwijt tegen de moes. Ik moet tegen de moes maken een keer tegenrijden. Dan mag ik geen schroeven, niet. We gaan ook binnenrijden, niet.
Eugène moet zowat de handigste chauffeur van Vlaanderen zijn. Het is letterlijk rijden tot op de millimeter. En zelfs als de auto binnen staat, moet hij er nog altijd uit geraken.
Voilà, ik doe ik mijn deurken open, zie. En dan moet ik mijn deurken van mijn not open doen, want anders kan ik niet meer uitstappen, niet. Voilà, en zie dat ik geen blusje maak. Auto kan stil liggen, uitstappen, de wagen vooruit duwen.
So this short video was to show you how big is 5 feet. Then the next chapter is geostopping, and it has in it a safety moment. You will see, it's quite interesting. So geostopping with a safety moment, resistivity at beat, and looking ahead of the beat. Geostopping was, in fact, I probably co-authored the paper in the mid-80s on the ability of measuring the resistivity at beat. I was not the inventor, but I was a co-author on the paper. But the technology has been around since the mid-80s, 1985, 86, etc. So here is a situation where you can measure the resistivity at the beat if you are in oil-based mud, or near the beat if you are in water-based mud. And what's interesting is that it will let you know right away in minutes or in hours, well, fractions of an hour, that you have crossed a boundary that, whether you were expecting it or not, and you may decide at that point that it's urgent to stop, and that's why it's called geostopping. We are not the only industry who uses resistivity to make a decision to stop. There is a company.
So I am going to run this veggie hot dog through the saw with a slow motion camera so you can see this technology in action. Here we go. Whoa, that's how fast that happens. That is insane. That's the mark on the hot dog.
So you see, the idea of geostopping came to a company called SawStop, which said, why don't we use the resistivity of the finger or a hot dog to stop a saw before it starts doing some serious damage? Geostopping has become even more advanced recently. That's, let's say, 40 years since the first paper, by the ability to look ahead of the bit and be able to recognize an approaching boundary before you even hit it. And that's pretty challenging and pretty important. I cite here a paper in Petrophysics, volume 66, number 2. It's a joint publication between Schlumberger and Petrobras, where they look ahead of the bit and they can identify an approaching boundary ahead of the bit. So it's called Look Ahead of Drilling Technology Assessment for Early Hazard Identification in Pre-salt Offshore Brazil. So this is technology is extremely more advanced than simply geostopping, but it is one form of being able to recognize a fault, let's say, ahead of the beat in a horizontal well or a vertical well. So here we have the end of the chapter. We have showed resistivity logging and water saturation. We have discussed laminated reservoir. We have discussed borehole imaging with resistivity. We have discussed on the macro scale, well placement, geosteering, reservoir mapping, and geostopping with resistivity at beat and looking ahead of the beat. So here, this is the end of the SPWLA Nuggets of Wisdom, the wonderful of resistivity from the micro scale to the macro scale. My name is Roland Chemali. I'm a technology consultant for Well ID, and you have my contacts here. Please feel free to ask any question I have. I'd be very glad to answer